Let's begin. So just as a reminder, project number 4 is due on Tuesday, November 6th, so 1 week from today. We will spend part of the class period discussing project number 4 some more. Test number 2 is officially going to be 2 weeks from today, Tuesday, November 13th. Are there any questions before we get going here? Okay. We left off last time talking about qualitative predictor variables and how we can include them in a regression model. In particular, we were in the middle of this example involving the car highway miles per gallon, where we were trying to use the class of the car, which was a qualitative variable with 7 levels, using that to predict the corresponding miles per gallon. So in particular, our model looks something like this. Get my red pen out. We use the model of this form. Expected value of MPG, miles per gallon, that's our response, is equal to beta 0 plus beta 1 times x1, where x1 was an indicator variable corresponding to compact cars. Let me just rearrange the stuff that's in this table corresponding to what we had originally. There we go. So x1 is the indicator variable for, in case I said compact cars, I meant large cars, plus beta 2 times x2, which is the indicator variable for mid-sized cars. And we can keep on going all the way down to beta 6 times x6 for 2-seaters. So for example, x1 is equal to 1 if it's a large car, 0 otherwise. Notice that we had 7 levels of this class variable and only 6 indicator variables were needed to represent it in the model. The compact classification has values of 0 for all indicator variables. So that if I wanted to write out, well, what is the expected value of MPG in terms of compact cars, in terms of our model, it's just simply beta 0. So that's for compact. For large cars, expected value of MPG is equal to beta 0 plus beta 1 times 1 plus, and then no other terms in the model. So all the rest of the indicator variables are 0. So that's for large cars. So essentially what we're saying is the mean value for compact cars is beta 0. The mean value for large cars is beta 0 plus beta 1. So that then, if I were interested in, let's say, taking mu sub MPG, redo this. Suppose mu represents the expected value of MPG. If I were to say mu sub large, so the mean for large cars minus the mean for compact cars, what do I get in terms of my regression model? It's okay to speak up.
Beta 1, X1.
Beta 1. X1 will be 1. So if I did a t-test, let's say for beta 1 is equal to 0 versus beta 1 does not equal 0, it does not test the significance, let's say, of the large classification. Rather, it tests a contrast between the mean for large and the mean for compact. You could do a similar thing for beta 2. It's going to test mean for mid-size versus the mean for compact. Keep on going down to 2-seater if you wanted to. Okay. How do I actually then estimate these models in R? Well, it's fairly simple. There we go. Just use the LM function, formula equal MPG tilde class. And R automatically creates all these indicator variables for us. So for example, this negative 0.50 that's highlighted in blue is B1. Then the p-value of 3.25 times 10 to the negative fifth tests what? Tests whether or not beta 1 is equal to 0 or not, meaning it tests, yeah, so mu large minus mu compact. Is that equal to 0 or not? So is there sufficient evidence to indicate a difference in the means between large cars and compact cars? Yes or no? I see one person responding. Yes. I don't see. Thank you. Yes, there is. But now you might be interested, well, suppose I wanted to compare large to mid-sized cars. You know, based upon what we have here, we can't do a direct comparison. So what we talked about last time towards the end of class was two ways that you could make that comparison. One way was to use the relevel function, which changes what the base level or reference level is for our qualitative variable class. So previously it's been compact. If I wanted to change it to large, I could do that by using the relevel function. Another way that we were starting to talk about was to use the mult-comp package. And in this particular case, what we can do is actually code in the direct comparison that we want. So in this particular case, if I want to compare large to mid-sized cars, what that essentially means then, and I'm not going to go through all the details like we did last time, I need beta 1 minus beta 2. I want to do a hypothesis test to see if that's equal to 0 or not. And the mult-comp package provides me a convenient way to do this. In particular, just as a review, let me do some erasing here so we can see this better. In particular, what I need to do is write what we call a contrast in order to do this test. So let's let K get a matrix where now I'm going to write in 0, 1, negative 1, 0, 0, 0, 0, which corresponds to, if I were to take that corresponding vector then, times my beta vector, I get beta 1 minus beta 2. Say number of rows 1, number of columns 7. I use the GLHT function to do some preliminary calculations, and then use the summary function to actually do the test for me. So as I have marked on here already from last time, B1 minus, that's not a good color to choose. B1 minus B2 is negative 2.634. So that's the estimate of beta 1 minus beta 2. We have the corresponding standard error, we have the corresponding t-test, and the p-value of 0.0284. So there's marginal evidence of a difference in means between large and mid-sized cars. Also last time we talked about how one could actually do multiple different calculations like this at the same time, where now we just enter in an additional row to my matrix. In particular, the second row here corresponds to the large versus compact car comparison. So notice it's just going to give you beta 2, and you apply that vector part of the matrix to the beta vector. And we get the same results as before. Notice this negative 0.5009. That's the same estimate as we saw previously, eventually when I get there, as we saw right here. Okay? So that leaves us then to where we left off last time. Again, unfortunately, it was in the middle of this example. Yes?
In the one where you're testing both the large versus mid-size and compact, why the second row of the vector, why is just the constant 0, 1, and 0.
Because in the context of our original model, remember that compact was the base or reference category. So don't get that confused with what we did with the with the re-level function. Okay. Now you can do other tests too. You can do a whole bunch of tests, but whenever you do tests like this, you might be worried about the family-wise error rate. We talked about the family-wise confidence level way back in Chapter 4. Remember what that represents. If I have, let's say, G different confidence intervals, each confidence interval, let's say it's at a particular confidence level, the overall confidence level of all these confidence intervals I'm doing is not the same as the individual levels. So, for example, let me get Windows Journal up. So, let's say and this was the original example that we looked at, if I did a confidence interval for, I can't write. If I did a confidence interval for beta 0 in a simple linear regression model, this was the formula that we saw. And then a confidence interval for beta 1. Each of these are at the level of 1 minus times 100% confidence. But the confidence level that both these intervals works is not 1 minus times 100%. And so what did we do to control the overall confidence level, the family-wise confidence level?
Divide alpha.
By what?
T is like a number of
G, the number of intervals. In this case, it just happens to be 2. The number of intervals that you're doing. Okay. So that's with respect to, that's called a Bonferroni correction or Bonferroni adjustment. But now, let's say that I want to apply the same idea now with hypothesis testing. With hypothesis testing, what are you concerned about? Type 1 error rate, which we denote by alpha. So every hypothesis test that you do has a type 1 error rate of alpha. Well, if you do, let's say, G different hypothesis tests, it doesn't mean that overall your probability of making a type 1 error is alpha. No, it's not that. But what we can do is do a Bonferroni correction so that we can say that the type 1 error rate is, let's say, no larger than alpha. So let's talk about how we can do that in the context of these models. So the code here, this is now new material, the code here is exactly the same as what we saw before, above, except for this right here. If you remember, in the summary function, there is an argument called test. And so far we have been using test is equal to adjusted parentheses, quote, none. Meaning no adjustments at all to these p-values at all to account for the fact, or to account for the family-wise error rate. If I put Bonferroni here, I get a Bonferroni correction. Okay. Well, let's compare now this output that we get once we do that to what we had above. What's the difference between the two sets of output? These p-values are different. Excuse me? The standard errors are the same. 1.197, 1.197. So the p-values are different. How are they different? What was done, do you think? It goes back to your days of multiplication. what was done. And multiplied by 2. We had 2 tests. The p-values are now multiplied by 2. You should think about on your own, why are we multiplying the values by 2? Compare that to what we were doing back in chapter 4. Maybe that might be a good test question. So what we can do now here is just simply compare these p-values now to our type 1 error level, whatever we say. Maybe it's 0.05. That's how we do this comparison, or to make a judgment of significance. An alternative way to do a Bonferroni correction would be to simply stick with the original set of output that you have, but rather than comparing each of these numbers to alpha, compare it to alpha divided by g, where g will be 2 in this case. That will be equivalent. So this is a Bonferroni adjustment or Bonferroni correction applied to a situation where now you're doing hypothesis tests. Are there any questions? Okay. Page 838, we've already basically discussed this. This is just to emphasize that a regression, an ANOVA model that all of you should have seen, at least if you took Stat 801, an ANOVA model is equivalent to a regression model. This is now put into the context of this car miles per gallon example. Okay, page 839. Well, what would happen if, let's say, we had a qualitative variable in our data set, but it was coded numerically? This often occurs in applications. So maybe with the class of the car, it was coded compact had a level of 1. Large had a level of 2. So that you had numerical coding of all the different classes. Well, what would happen then if you said in your LM function, formula equal MPG tilde class? R would not know that indeed that class was actually qualitative, that these numbers actually had a category meaning, and would treat this as a numerical value and would estimate beta 0 and would estimate a beta 1, and that's it. It would treat class as numeric. So how could you then tell R that, no, this is actually a qualitative variable? These numbers in that ordering, 1, 2, 3, 4, 5, 6, 7, has no meaning at all. What you could do is this. Say factor class. There's a function R called factor, which tells R treat this as a qualitative variable. Some people might call them factors. Especially if you had a class like Stat 802, you call them factors in that class. So let's take a look at an example of what happens when we do this. In this car data set, there is a variable called cylinders, for the number of cylinders of an engine. Now that is numeric. It's supposed to be numeric. You know, if you have a 4-cylinder versus 6-cylinder car, well, yes, indeed, you do have less cylinders with 4 rather than 6. But just for illustration purposes, let's ask R to treat this as a qualitative variable. So to begin with here, I estimate the model that treats cylinders actually as a quantitative or numerical variable. This is the output that we get. Notice that we have a negative value there for the slope parameter. Does that make sense to have a negative value? Some people say yes. Why would it make sense? what kinds of cars typically have a high number of cylinders? Sports cars, big cars. Are they going to have good gas mileage? No. You have a smaller number of cylinders. Typically you have small cars, kinds of cars that have a lot better gas mileage. So yes, it does make sense to have a negative coefficient there. Or, wait a second. Let me restate that. No, that does not make sense. Am I thinking about this wrong? It was making sense to me when I was going over my lecture earlier today. Oh, yes, it does make sense. Because, of course, as cylinders increases, that's going to cause then your, let's say, your MPG hat to decrease. Sorry about that. So let's actually use the factor here with cylinders. Now, in the data set, there happens to be 3-cylinder, 4-cylinder, 5-cylinder, 6-cylinder, 8-cylinder, and 12-cylinder cars. Wow. So, what do we see here? We see indicator variables representing these different number of cylinders. Notice how R does its coding for the indicator variables. 3 is the base or reference level, because 3 comes before 4. So remember, as I mentioned before, R puts everything in alphabetical order, where numbers would actually come first in a numerical order if numbers represented levels of a qualitative variable. Let's take a look at this now. Look at the ordering here. So as the number of cylinders goes up, that corresponding B goes down. Does this make sense? Generally speaking, the B goes down. There's one exception. Does this make sense? Yeah, because again, as the number of cylinders goes up, you would expect your miles per gallon to go down. And that indeed is shown here. Just to show you, well, what does this factor function do? I actually applied factor outside of the LM function to the cylinders variable, and you just see a listing of our data, but this is the key part right here, levels. So what R says, okay, it's going to transform this to a qualitative variable, and it lists all the particular levels, unique levels out, 3 through 12. As we saw before, one could use the contrast function to see how R will actually code this in terms of indicator variables. Okay, and that concludes that section. Are there any questions? Okay, why don't you take out your project so we can talk about that? Yes?
Is it possible to have like an example of matrix?
Excuse me?
Like a matrix form of this. The matrix form.
Okay. Well, what would happen in the matrix form is this. I think you're talking about what does the X matrix look like?
Yes.
Okay. So let's just look at, let's say we'll look at the first 3 observations. Obviously, the first column is all going to be 1s. And then let's say that the first car in this data set was large. Okay? So we're going back to the class of the car example. So notice we had an indicator variable for large, mid-size, down to 2-seater. So if the first car had a large classification, you have a 1 here, 0, and then 0s all the way across. If the second car in the data set was compact, you would have 0s all the way across. And that's what your X matrix would look like. Does that answer your question?
And we only use the same formula of beta.
X prime X inverse, X prime Y. Yep. Yep. Any other questions? Okay. Let's take a look at the project. So let's go look at number 2. Now I think there's 3 of you in this class that actually took my Stat 801 course last fall. And I had a similar, but not the same, example in that. I purposely chose this particular, I should say example, it was actually a problem on a project. I purposely chose to do this particular problem to help those few of you, to help emphasize how regression models and ANOVA models are the same. You looked at it in terms of an ANOVA model in Set 801. Okay, so here's the setup for problem number 2. Now, in order to maximize sales of items at a grocery store, the manager of the grocery store is going to have items placed in certain locations to try to draw customers' attention to them so that they'll put it in their basket and then go buy it. Okay? And we're going to look at one particular, let's say, region or one particular kind of item at grocery stores, in particular, breakfast cereal. Okay. Now, typically in large grocery stores, breakfast cereal is arranged in one aisle on one side, and you have maybe 4 or 5 shelves of the breakfast cereal. This is in particular the aisle at 27th, or at the high V at around 27th and Superior in Lincoln. And so we can see, let's say we have a bottom shelf here. I can't write on here, unfortunately. Let's call that shelf 1. We have a top shelf. We'll call that shelf 5. Now, where these the grocery stores put the cereals on these shelves, or they put it on the bottom versus the top, I hypothesize is done by a plan to try to get people to buy certain kinds of cereals. Okay? So what I did a few years ago, not at this Hy-Vee, I took a random sample, a stratified random sample of cereals at a particular grocery store, where I took a sample size of 10 within each shelf, so stratified by shelf. So my first item that I got was Kellogg's Razzle Dazzle Rice Krispies. It had a serving size of 28, and what I wanted to focus on was the sugar content. And 10 of the grams of the serving size of 28, 10 were sugar. High sugar content cereal. In particular, 0.357 or 35% is the amount of sugar content. Also on shelf 1, this is the lowest shelf, Post Toasties Corn Flakes, same serving size. Sugar's a lot less, 7% of the content. And I did this, there was only 4 shelves at this particular grocery store. So 4 was the top, 1 was the bottom. And what I was curious about is, do they place cereals with respect to the shelves based upon the sugar content in the cereals? Now, why do you think I might be interested in something like that? Because I had a lot of free time on my hands and I just wanted to take a sample?
Children.
Children, yes. What shelves do you think children might, let's say, want their high sugar content cereals to be on? 1 and 2, the bottom shelves. Because they can easily grab it, because they can't go up to shelf 4 and grab it off. But they can easily go off shelf 1 and 2 and put it in their parents' basket. Now, just as a quick test, I happen to have 2 children of my own. My oldest son, Callum, he is 3.5 years old, and I had him go down the cereal aisle when he was 2.5, and I shot a little video. My wife's behind the camera, so there's Callum. He is very. It's kind of hard to see, but he has very bright red hair. I don't have red hair. My wife doesn't have red hair. We were shocked when he came out with red hair. And then we went, oh yeah, both grandmas at one time had red hair. So anyway, so this is Cal, and I said to him, go down the aisle, see what happens. And let's just see what happens. So he's looking. Oh, some good cereal there. Let's see if I can find some. And he picks out Cocoa Crisp, which is a very, very high sugar content cereal. And I said, well, go ahead, Cal. You pick out some more. Cocoa Puffs. And Cocoa Puffs again. Oh, this is not going to be good if he eats any of that because he's going to have one big sugar high. And so that shows you that indeed if you put it on shelves 1 and 2, it's in reach of the children. And so that's what you often see is these cereals that are focused on children, which typically have high sugar content, are on the lower shelves. So that's my research hypothesis that is true. So how can we test that? That was why I took this sample, and that's why you're going to do this project, is actually to test that. So part A here, construct a box and dot plot of the data. Does there appear to be differences in sugar content amongst the shelves? I'm sorry, let me back up a second here. So sugar content per gram is your response variable, and shelf number is the predictor variable. Okay. Given that, let's do a box and dot plot of the data. So this is very similar to what we did earlier in the notes. You find the corresponding place since it was a few days ago. When we did this with respect to the car miles per gallon data. Basically, do this now for this the sugar content in cereal data, and then look at it from just look at the plot. Do you think that there might be differences in the sugar content based upon the shelf location? You know, make a general judgment. Part B. Now find the sample regression model. So again, shelf is the predictor variable. Sugar content is the response. Part C, perform one hypothesis test to determine if there's a difference among mean sugar contents of the shelves. What type of test? What's the name of the test do you think you're going to use here? Looking for one overall test. Thank you. Overall F test. Exactly. So you're going to do one overall F test. And then typically in situations like this, if you reject, then you want to determine, well, what caused it to reject? Which shelves are actually different? And so that's the purpose of part D. What I want you to do is do all pairwise comparisons of the mean sugar contents for these shelves. How can you do this? Well, one way is to use the mulch comp package that we just talked about earlier today. Another way is that you could fit the model using all the defaults, and you will get the corresponding test statistics for those 3 top tests. And how would you get the other ones?
Have to put another variable like a comparison, change.
Yeah, change the reference level. Re-estimate the model, get the test statistics out. So that's another way you could do it. I think the mulch comp package is maybe, well, in the end it's maybe a little bit more difficult to set everything up, but at least everything's going to be more compact in how you're doing everything. So, pick one of those ways, list out all the test statistics, list out all the p-values, and interpret this table. Where were there main differences? Part E, add a column to the table now for a Bonferroni corrected p-value, just like what we did. Do your overall conclusions change? And then lastly, part F, relate your answers to D and E here, where we're finding population mean differences. Relate them to what you saw previously in the plot. Do your conclusions here make sense? That's what I'm looking for. Okay, so that's problem number 2 on the project. Are there any questions? Yes.
Yes, and again, why is it impossible to use a t-test?
Why is it what?
Why is it impossible to use a t-test?
Well, you're using t-tests here.
I mean, for a single, like to test the significance of new one.
I think what you're getting at is, why can't we just simply look at, in this case, it's there are 4 shelves. In the default output that you get, there's going to be 3 t-tests, right? Okay. So why can't we look at just those 3 t-tests to make an overall conclusion? Well, I think the answer is obvious here. You're missing out on 3 of them here. There's 6 total. And so the overall F test then allows you then to look at all. Are there any differences? Okay. Other questions? Okay. So there's still 1A on the project that we still need to discuss. We'll discuss that once we do some Chapter 9 material that corresponds to it. Okay, that takes us to page 842. So I'm kind of just combining some stuff here. Modeling interactions between quantitative and qualitative variables in more complex models. Essentially what this section is looking at is this. Suppose we have some quantitative variables, maybe some qualitative variables as well. How do we include, let's say, interactions between the quantitative and qualitative? How do we include interactions between 2 qualitative variables as well? That's what this section talks about. And it's really not that difficult to include these interactions. Let's take a look at a simple case of the following situation. Expected value of y is equal to beta 0 plus beta 1 times x1 plus beta 2 times x2. If x1 and x2 were both quantitative, maybe let's say continuous predictor variables, if I wanted an interaction between the 2, I simply put this in the model. So again, what the interaction is saying to you is the effect that x1 has on the response is dependent upon the level of x2. And you could change that also in terms of the effect of x2 on the response is dependent upon the level of x1. That's what an interaction is. Now let's say that we had a qualitative variable and it had levels of A, B, and C. Okay? We still also have this variable x1. Then we could write our model like this. Expected value of y is equal to beta 0 plus beta 1 times x1 plus beta 2 times b plus beta 3 times c, where b is an indicator variable corresponding to level B. C is the indicator variable corresponding to level C. Okay? If I want to now include an interaction between x1 and this qualitative variable, all I need to do is this. Beta 4 times x1 times b plus beta 5 times x1 times c. So all you do is you multiply each of the indicator variables by the corresponding quantitative variable. That's it. Not that difficult. Suppose instead I had this qualitative variable with levels A, B, and C, but also I had another qualitative variable with levels X. Oh, I don't want to put X there. Let's say with what letters do I want to use? F, G, and H. And then I can write my model like this. Okay. Now, if I want to include interactions, what do you think is going to happen? What did I do for the quantitative variable? Took the quantitative variable times all levels of the qualitative variable, or times all the indicator variables. What do you think is going to happen here? Just going to multiply all the indicator variables together. That's it. You should think about how your X matrix, how that looks as well, corresponding to a question that we had earlier. So in general, if I had, let's say, let's actually go to the notes now. Amongst the notes. So in general, let's say the first qualitative variable had C levels to it. The second qualitative variable had D levels to it. Then there are C minus 1 times D minus 1 terms needed to represent that interaction. Let's take a look at an example. So a car highway miles per gallon again. I'm simply going to look at engine, which was quantitative, which was the size of the engine, number of liters, and the class of the car once again. And so I'm going to estimate a model that has engine in it, class. To do the interaction, all I need to say is engine, class. It automatically does all the multiplication for you. So here's the output. Oops. So we see the estimate for engine, we see the estimates for class, and then we have the estimates of the B's for the interaction. So notice we can, and when we include these interactions in a model with a qualitative variable, you can get a lot of parameters being estimated. Of course, depending upon the number of levels of your qualitative variable. So what does this model look like then, if I were to actually write it out? There it is, kind of long. So again, here is the B for engine, and then we have all the terms for class. Again, I could call these the main effects, and then the corresponding interactions are listed here. So that 2.6877 corresponds to this right up here. So let's say I want to determine, is this interaction helpful to me or not? How could I make that determination? Do a partial F-test. Do a partial F-test where you test all the beta coefficients on the interactions. So first of all, to do this then, I'm going to estimate my model with just engine and class in it. And then, using what we've learned previously, I can use the ANOVA function where I put first the reduced model, and then second I put the complete model. R does all the nice calculations for you. Here's the F star test statistic, and here's my p-value. Notice it's small, indicating, yes, indeed, this interaction is helpful. More formally, we could write this in terms of our hypotheses. So the 8th beta down to the 13th beta are all set equal to 0 under the null hypothesis. Just that if they were 0, we wouldn't have the interaction in the model. The alternative hypothesis then is at least one of the betas does not equal 0. So there's at least some type of interaction going on. We don't specify where, we just specify there's at least some. State my F test statistic, the p-value. Suppose I use alpha 0.05, p-value is less than alpha, reject. What does this mean? There is sufficient evidence to indicate an interaction between engine and class is important. Okay. Yes?
Is there some rule of thumb for the number of parameters you're estimating to the number of observations you have?
Some people have stated rules of thumb, yes. And that's actually kind of a research topic in statistics, and that is compare your P to your N. So often you'll see in statistics research papers actually done on large P, small n problems. Generally speaking, for the stuff that we're doing in this class, you're going to need to have P to be less than n. Otherwise, your X matrix is just not going to, when you do X prime X inverse, it's not going to work out.
Okay.
And there are various rules of thumb, and there might be a rule of thumb mentioned in our book, but it varies from person to person.
Right.
Okay, so we got this hypothesis test result. It says that interaction is needed. Well, let's actually look at some graphs that actually help us see why this interaction was truly needed. And so what I like to do is actually apply to the model. Now you might be thinking, okay, I have engine, I have class, and then also I have MPG, so that means I have to go 3 dimensions here to do this plot. But no, that's not true. The reason being is because since one of these variables is qualitative in nature, what I can do is condition on a value of the category, in this case for class, and then graph this in 2 dimensions, MPG versus engine. So, in particular, let's look at the compact class of a car. If I want to see what the model would be for a compact class of the car, what that means is all the indicator variables in there are all equal to 0. And what am I left with? Just simply this. So the regression model, when I have a compact car, it's just simply MPG heck is equal to 41.1 minus 4.4 times engine. That's it. If I want to look at, well, what's my model when I have a large car? Well, again, I have B0 plus B1 times engine. But now I have to worry about when large is equal to 1. So let me get a highlighter out here. So here's large, and here's large as well. All the other indicator variables that are not highlighted are going to be 0. So I can simply write those corresponding terms in here, do a little math, and notice it's just a function of engine now. And in fact, I could do that for all the levels of my class variable, and now do a plot. Go over here to 10. Okay, first what I want to do is do the graph for compact. And so I use the curve function to plot the model. Curve equal, my expression is equal to B0 plus B1 times X, and that's it. Put a nice little color, put line type, put some labels on my plot, and there's my model for compact cars only. I can do the same thing for large cars. B0 plus B1 times X, and then here's B2, because this corresponded to large cars, plus then the corresponding B for the interaction term times engine. Make it a color of blue. And there is the model for the large cars. And I can keep on going. And I'm just going to jump over here to Word because the plot's already there. And this is what I get. So from this plot, we see why the interaction was needed. Remember what the definition of an interaction is. How one variable, let's say engine, affects the response is dependent on another variable, let's call it class. Well, we see the dependency here. The extreme case is look at station wagon, which is in black. So it's this line here. And compare that to two-seaters, which is in brown. So there's the line there. Notice how the effect that engine has on the estimated MPG changes based upon if it's a two-seater or if it's a station wagon. We see that by the different slopes of the line. That's why the interaction was needed. That's why the interaction came up to be significant. What would you expect this plot to look like if the interaction was not significant? Each of the lines would have what? The same slope. Yeah. So the lines essentially would be parallel to each other. For those of you who have taken Stat 802, you probably saw something very similar to this when you did a treatment means plot, let's say for multi-factor experiments. You look, were the lines that you would graph, were they parallel or not? And that will tell you whether or not the interaction was needed. Same concept here. Is there extrapolation beyond the range of the engine sizes? Well, remember what we learned back in Chapter 1. You don't want to extrapolate your predictions beyond the range of your predictor variable. So in this case, what does that mean for us here? Take station wagon. Look at the range of the engine sizes for station wagon and only do the prediction for those between the minimum and the maximum. Also look at large cars. Find the minimum engine size, find the maximum, do your prediction there. So is there extrapolation? Yes, there is, but it was sure easier to draw the plot like this. Okay. What would I do in actual application? I would actually change where those lines occur based upon the minimum and maximum for each of the engine sizes by class level. Also, another reason why I did a plot like this was because I knew I was going to do this plot too. So now what I did, and you can take a look at the code in the program itself, I actually plotted the data. And I color-coded each of the plotting points by the same color for the class of the car, and also I used different symbols for each class type so that you can see what's going on in this plot. Now, I admit that there's a lot going on in this plot, so it can be difficult to see, but you can, generally speaking, if we, let's say, focus on large cars here. So here's some large cars, here's some large cars, here's some, here's some, here's some, here's some here. And you can see that, generally speaking, the blue line for large cars is going through the middle of those points. To help see this better, I did another plot. And here we go. Now, I didn't allow the line to go beyond the range of their corresponding values. Hopefully people who interpret this plot realize that you shouldn't interpret for, let's say, station wagon. You shouldn't interpret that down there. Hopefully. But here you can now see how these lines are going through the middle of the corresponding points by the class of the car. Which again just emphasizes stuff from Chapter 1, what least squares estimation gives us. Okay. Any questions? Lastly, on page 848, residual versus indicator variable plots are not necessary. First of all, let's talk about these residual plots. If I did typically we do residual versus predictor variable plots to get a general sense of have we misspecified the form of the predictor variable in the model. So you might be thinking, well, then we would want to do residual versus indicator variable plots. Well, no, you wouldn't want to do that. The reason being is because the only way that we can include a qualitative variable in our model is with an indicator variable. Also, you can think of it this way. If you have an indicator variable x1, would it make sense to have x1 squared in your model? No. Fortunately, I had one person respond. But no, because 0 squared is 0. 1 squared is 1. So no, it doesn't make sense to do transformations of those variables. So don't look at residual versus indicator variable. But in another class, you may have heard of stuff called analysis of covariance models or ANCOVA models. Essentially, this is what we just did with this example here. Okay. And that concludes Chapter 8. Let's go to Chapter 9. So Chapters 9 and 10 focus on building the regression model, or you could say model building, meaning that you have some variables, some predictive variables, and you have a response variable. You need to decide which predictive variables to include in the model and in what form they should be in the model. Overall, our goal is this. Find the most parsimonious model that best estimates the response variable. I know when I took a class like this, my professor said that same goal, and I had to look up, what does parsimonious mean? Parsimonious means that you want the model to be basically as small as possible, to contain the least number of predictive variables as possible, but still give you a very, very, very good estimate of your predictor variable. I'm sorry, of your response variable. So we want small models, but good models. That's our goal. Well, how can we decide then, well, what predictive variables to include, or what form the predictive variables should be in? Well, that was kind of the purpose of chapters 1 through 8. We learned a bunch of tools that help us make these decisions. You know, t-tests, partial f-tests, adjusted r-squared, doing various diagnostic measures. We learned all these tools to help us decide what the model should look like. We're going to put all these tools now together in chapters 9 and chapters 10 so that by the end of chapter 10, you're set to go after this class. If you're given a problem where regression analysis is needed, you could do it from start to finish. Okay. Section 9.1 just gives an overview of the model building process. Step 1, well, got to have data. Go collect your data. Make sure there's no data entry errors and stuff like that. Okay. Step 2, this is the one that we are going to focus on in this particular chapter. Reduction of predictive variables. Oftentimes, you collect more predictive information on more predictive variables than what you really need. Well, how do you sort through these predictive variables then to choose, yes, I want to use this one further, or no, I'm just going to throw this one away. I'm not going to use it at all. That's what we're going to talk about in this particular chapter. Look at some ways to make the decision. Step 3, model refinement and selection. This corresponds to stuff that we were doing, for example, in Chapter 3 and also in Chapter 7. Remember those functions that I gave you that allowed you to do a whole bunch of plots, to allow you to look at residuals, to make judgments about normality, constant variance, and stuff like that? That's 3. Also in 3, we make judgments of, well, do I need maybe some kind of interaction term? And then number 4 is called model validation. So from steps 1 through 3, you have found one model to use. Now you want to make sure, does this model work as you expect? So you validate the model. This is section 9.6. Since this is the last step of the model building process, I think it's good to talk about it after we talk about step 2, which is the rest of chapter 9, step 3, which is chapter 10. So what we're going to do is hold off on section 9.6 until we get done with chapter 10. Okay, so that's where we're going. This is the big picture. Okay, section 9.3. We're going to look at ways that we can sort through predictive variables that we have available to us to decide which ones we want to consider further for inclusion into a final regression model. We're going to look at a number of different criteria that one can use to decide between one variable or another. I've given you some tools. Well, I've given you the tools, most of the tools to do this already. And I purposely, when we were talking about these tools, is kind of tried to foreshadow what we were going to do now. So hopefully, when you see some of this stuff, you'll be saying, "Oh yeah, we kind of did this before." Okay, now I see why we were doing that. Okay. Let's consider situations where we have, and I didn't pick this notation, this is the book's notation, capital P minus 1 total predictive variables to consider. Okay, so capital P minus 1. And what we're going to do is look at subsets of those predictor variables. These subsets have little p minus 1 different predictor variables. So notice the book uses little p minus 1 to correspond to what we have used for our general notation when we write out a regression model. You know, there are little p minus 1 predictor variables in it. And to make things easy for us for now, let's assume that each of these variables is quantitative in nature. So no qualitative variables. Also, typically at this stage, one only considers models that have just first order terms, meaning x1, x2, x3, not x1 times x2, no interactions, not x1 squared. We're just going to consider first order terms. I'll tell you what you can do about if there was an interaction or maybe a quadratic term that you wanted to consider at this stage too. Okay. What we're going to do is this. Examine all possible regression models so you determine a set of models that are good to consider further. So, in the simple case of this, we have three predictor variables, x1, x2, and x3. Maybe these are the three predictor variables for the cheese data. Guess what, you're going to get to do some of this stuff for project number 4. All possible models to look at include the model that has no predictor variables. Maybe none of them are important. The model that has just maybe x1 in it. Or maybe the model that just has x3 in it. Maybe the model that has x1 and x2 in it. And in fact, in total, there are 8 different possible models that one could look at. And we want to look at which of these models seem to be relatively good so that we can refine them later on. The total number of possible models then will be 2 to the capital P minus 1. So in this case, capital P minus 1 is 3. So 2 to the third power is 8. Well, how do we make a judgment of, well, which models are good? Well, we can look at a number of different things. First of all, we can look at R squared, the coefficient of determination. And we know that, good models have, let's say, large R squares compared to other models. So a model that has maybe the largest R squared might be the best model, or might be models that have large R squares overall in comparison to all the rest might be good models. So notice the notation. This is the book's notation. In the book, they put a little subscript P on R squared to emphasize the number of predictor variables that are being used for a particular model. So if I have a model that has 2 predictor variables in it, R would denote this as R squared with a subscript 3, indicating there are 3 parameters being estimated. One could also look at SSE. Well, of course, sum of squared errors. We want that to be as small as possible. So how about we look for models that have a small SSE? Those are good models. In fact, looking at either R squared or SSE are actually equivalent. Here's why. This is our R squared equation. Rewrite it so that it's 1 minus SSE over SSTO. Now, if you're evaluating a number of different models, Is your SSTO going to change from one model to the next? Remember what SSTO looks like. The sum from I equal 1 to n, yi minus y bar squared. Will that change from one model to the next? No, because y bar is just the sample mean. X doesn't, none of the x's actually play a role. So the only thing that would change is SSE. And because of that, that's why looking at large R squared or looking at small SSE is equivalent. Now, you also hopefully remember from chapter 6 that there's actually a problem with looking at R squared. Because I could keep on adding predictor variables to my model, and R squared is going to go up, 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 up. It's never going to go down. So because of that, you can't necessarily look at a model that has the largest R squared. Rather, what you do is you look for a point where the R squares start to level off as a function of your predictor variables. Here's a plot demonstrating that. So let's say that we're looking at models. We're looking at a bunch of models. Some models have one predictor variable in it. Some models have two predictor variables in it, and so on. And for each model, I calculate R squared. And I simply plot the R squared versus the number of predictor variables. Notice if I were to draw a line on top of here, you can see how things are starting to level off once you get to 3 predictor variables. What then that suggests then is that maybe this model here, or maybe even this model here, might be good to consider further. Obviously, you wouldn't want to consider this model because it has the lowest R squared of the bunch for the 3 predictor variables. And we want large R squared, but we don't want it to be artificially increased. And so that's why once we get up here, we see that the benefits from adding a 4th variable doesn't look to be too high, so you might just stick right around there with those particular models. Any questions about that? Yes?
Why not just use the R adjusted?
Well, thank you for leading me into my next discussion. We could also use the adjusted R squared as well. And the book's notation is R squared subscript A, but again, they put a P here to emphasize the number of parameters in your model. One could also equivalently look at mean square error as well. So we want models that have a large adjusted R squared or models that have a small mean square error. They are equivalent. Here's why. Here's my adjusted R squared equation that we first saw in chapter 6. I could rewrite it through doing some algebra. Again, SSTO is not going to change from one model to the next. N is not going to change, obviously. What changes is MSE, so that's why we can look at both of them and get the same results. So R squared, adjusted R squared, those, generally speaking, should make sense. Here are some other ways that we can make a decision between models to decide which are good models to consider further. There are going to be 3 more ways that we're going to talk about. The first one's called Mallow's CP criterion. It's kind of a strange, at first you might think, but it makes sense that this would be a reasonable approach. How about you, step 1, estimate a model that has all your predictor variables in it. So notice how I have a capital P minus 1 right here. Get your MSE. You can think of this as maybe your best overall estimate of sigma squared. Okay? Now for every model that's under consideration in terms of subsets of all your predictor variables, compute SSE for each of them. Notice how there is a little p in there. So you're going to actually be computing multiple SSEs. So like when we have 3 predictor variables, note that we had 8 different models, so you would have that many SSEs. Now, if I were to compute MSE now for this subset model. Of course, you just divide by n minus p, the SSE, you get MSE. Now, if this MSE is similar to the MSE that we had in step 1, look what would happen. Take the ratio of the SSE and the MSE. Plug in what SSE would be using this expression. Look what happens. These will basically cancel out if they are similar. And look what you're going to be left with, n minus p. So if a particular model of interest has a value for this ratio of n minus p, then it says, oh, that seems like a reasonably good model because I'm doing just as well with this model than if I were to use a model that had all predictor variables in it. There's one last step. The actual C sub p statistic that we look at actually subtracts off n minus 2p. Here's why. If this is n minus p, and I subtract off n minus 2p, what's going to happen? I get p. So it's just a small adjustment. P, your number of parameters. That's all. Please delete out the stuff that's on page 9.7. Just a different way to think about it. I don't think it's necessary. So what this means then for us is this. To determine if a particular model is, let's say, good, I look for a C sub p that's approximately equal to p. So again, for all your possible models, calculate the C sub p. Again, these models are going to have, you're going to have models with different values of p. But calculate all the C sub p's, compare it to the little p, the corresponding number of parameters in that model. If C sub p is approximately equal to p, this is a model that you want to consider further. Okay. I think this might be a good place to stop. Are there any questions? Okay, then that's it for today.